So my name is Scott Harkins. This is your Multistack MagLev flooded chiller. And what building are we in?
Berry.
Berry?
Berry
Yeah,
building.
so we're in Berry building, and we're going to do the training on the oil-free magnetic levitating flooded chiller. So you have two compressors, turbo core. Each one of those compressors is a oil-free centrifugal, has a motor on a shaft with an impeller attached to the front of that shaft. And basically all we do is, well, we pick that shaft up in a magnetic field and float it with no metal on metal contact, and we speed up, slow down to speed up and slow down the impeller in the front. The only other moving part in that machine is the inlet guide vanes in the front, just like any other true centrifugal. I don't know if you have a centrifugal on site here. Used to. Mm-hmm. So we're looking to trim the refrigerant flow with the inlet guide vanes, just turning vanes on the front of the compressor, that all of that big, and the impeller is a two-stage impeller, and about the same thing. It's about that long and about that big around, at two stages on the front of the shaft. So all the technology is maintaining that levitation with the magnets. It's a electromagnet that uses basically the theory of opposing magnets. So we take that round, we call it a bearing, even though it's just a magnet, it's a magnetic bearing, and we energize it in all directions so that we push on that shaft so that it stands up in the middle of that circle. Like a positive negative, when you push on a magnet, the other one pushes away.
Yeah.
That we're using that same principle, but we do it with electricity, and that's how we stand that up in the middle of that shaft, in the middle of that bearing. We're looking at it 6,000 times a second to make sure that we can do it, because we're spinning it in a high 17,000, 18,000 RPM range while this thing is in full production, maybe as high as 20,000 RPMs. So we're doing a lot to get that to happen. But what we do get is incredible efficiencies, because we have a very light spinning mass compared to a traditional centrifugal chiller that's got a 3-foot long flywheel. And so the real big thing is the efficiency. The spinning mass is so much lighter. It takes a whole lot less energy to get it up to speed. It takes a whole lot less energy to stop it. No metal on metal parts. No loss of efficiency through oil. So not having oil, we don't have to worry about things about oil heaters, or we don't have piping restrictions. Cycling's not an issue, because we're not worried about trapping oil in certain parts of the machine and then having it log and not work. No oil coolers, filters, none of all those things that would have been part of a regular chillers are out the window because there's no oil. So it's a huge chunk of maintenance that you toss out the door right automatically, not having oil in the machine. Being a flooded machine, we have two barrels, the condenser and the evaporator. The condenser's down bottom, the evaporator's up top. The compressors sit directly on the evaporator inside the same circuit. So what happens is, if one compressor is running, the other compressor is relying on this check valve to stop refrigerant from going through it the other direction and backspinning. So this check valve will only let refrigerant flow that way. And that's why on startup, if this compressor is running, then that compressor wants to come in. They both do this even when no compressor is running. This valve right here opens, lets refrigerant flow in a little circle right here at the compressor, so it can get up to speed without having to fight the pressure of the rest of the system. So right, it just doesn't like it because we've got that magnet. We're starting at a very low speed. There's no real torque. Only about a half an amp draw and startup for this machine. So you're not going to dim the lights every time you start a compressor or anything like that. And because of that, you get really high energy numbers even if you do a lot of cycling, compared to a chiller that was dimming the lights and bringing in double contactors and drawing 300 amps every time it started. So this guy spins in a circle, gas comes in the suction, up the discharge, right back out into the suction, so it gets up to speed. About 60 seconds in, this valve will start to close. As it closes, it pushes refrigerant this way into the system, and you'll hear this check valve give a couple, 2, 3, 4, 5 bangs, and then it's gone. Because not by that time the metal check is completely up this way, and it will sit there until this machine has pressure equalizing on both sides. If you lose your tower and it gets so high that this refrigerant pressure becomes so high that this can't push on, because this is just a pump. If you think about that chiller as a pump and not a piston, it'll make sense, because just like any other pump, if it can't push the column, it's going to start cavitating and skipping and spinning. So if that happens, this check valve will bang, because it's trying to push this way, it's fighting, getting pushed back, fighting, and you'll hear this bang, and a lot of times I'll ask them, I'll say, what's your cooling tower temp? And they'll say it's 117 degrees. I said, well, maybe we have a cooling tower issue, and we'll go there. So on the compressor, I was talking about the inlet guide vane. There's a little, looks like a fuel gauge right here. I don't know if you can see that with the camera. At the bottom is a BB. So that is the position of the inlet guide vane inside that machine. So it's good for diagnostics because I can say, you can say, hey, the compressor's running really low amps and I'm not doing any cooling. I'll say, what's the inlet guide vane position on the screen say, which I'll show in a minute, and you'll say it's 110%. I'll go, where's the BB in that? You go, it's all the way at the bottom. And I'll say, well, the inlet guide vane stopped working. And we're basically operating it with the ball valve close in front of it. So it's not pushing any refrigerant, but since it's a pump, it's just gonna spin. It won't overheat like a water pump because it doesn't have that pump friction as with water, like, you know, it's only Freon. Both compressors are completely isolatable, so you could work on that one while this one runs, so you shouldn't have to have downtime just because you have a compressor issue. They're gap shut off on all sides. The discharge got one, suction's got one, the economizer, which we'll talk about, has one. Right here is a ball valve, right here. And the liquid cooling line, which is on the back side, which we'll get to when we turn it on the back, also has isolation. So you could isolate this compressor. You could take it down and put a new one in if you had to. Hopefully we won't. Or you could work on any piece of it and keep the chiller running. So you've got good redundancy right there with having two compressors, and one can be serviced while the other runs. Let's see. We have components on this side before we flip to the other side. We have the sight glass for the evaporator and the sight glass for the condenser. So essentially at full load, you'll see refrigerant in both. At low load, you'll usually always see refrigerant in the condenser, but if it's not drawn hard enough, this refrigerant's gonna sit a little lower in this evap. So it's 70% demand with both compressors running or greater. Typically, we'll see refrigerant in this glass while it runs. But if it's got no load on it, it's just, you know, like a day like today, and we're running at minimum and cycling on, cycling off, you probably won't see any refrigerant in this glass. You will be cooling, but don't focus too heavy on that unless you're really running hard. If you're running hard and you're not making temp, then we're going to start looking at things like that. But what controls the levels on the other side, which we'll talk about after we talk about this guy. So this is I call this our service tech screen. Got a lot of info, a lot more than most people care to see. But if you're working on the chiller or have to perform some work or tuning it, it's a great screen. So this box right here tells you everything you want to know about what's going to happen next and what your temperatures are. So right now, system enables off, circuit not ready to start because the automation has the machine off. So nothing's going to run. So we have chill water out, chill water in temps, we have evaporator approach, and then we have condenser water in, condenser water out, and condenser approach. Approaches are the difference between, it's like superheat, but it's on water instead of Freon and suction. So it's the difference between leaving chill water temp and suction temperature. So we want that to be pretty close, 1, 2, 3, somewhere in that ballpark. If it gets too far out, we're not very efficient, which means we're either low on gas or we're maybe moving water too quickly, so we're not picking up as much heat as we should, or the chill's dirty, so it's not transferring heat as effective, things like that. So that number holds true on the condenser side too. So the discharge temperature versus leaving condenser water temp would be our approach. And that should be tight also, because if that starts to spread, same thing. We're either not moving water fast enough, or we're dirty, we're not transferring heat as we should, and the heat's not being rejected and it's building up in the chiller and causing issues. So everything here is in nice plain English. So our system start stop is your automation. So if that says off, we're not going to run. Emergency stop, I believe you guys have glass break here, so it's wide through the glass break, so that's on, which is a good thing. Flow switches, on and off, condenser and evap. High pressure, low pressure switch. There's one high pressure, one low pressure switch on the entire machine. The high pressure switch is right here on the pipe behind here, and it's got a manual reset button on it. This is your third stage of high pressure safety. So if this trips, something's happened quickly, like your tower literally is the fan belt broke, or something happened and we're not moving. But the first two stages are electronic, which are always slower than the button, but they're set lower. I think it's 185 for the chillers high pressure cutout. It's 205 for the electronic high pressure cutout, and this one's 215. It does not have a Schrader behind it. So if this one breaks, we can't just unscrew it and screw no one in, or we're going to have 800 pounds of gas on us real quick. That being said, there are ports, if you had to get one on it quickly, there's one on the ball valve right next to it that you could screw on the Schrader and at least get you going until you had to perform some maintenance. That's the only manual reset on the entire machine. Everything else is completely automatic reset. If we lose flow and then you regain flow, it's going to start up if it's being called for. There's no, you don't have to come in here and hit your resets or clear a button. Same thing with low pressure or standard high pressure. The low pressure switch is on. It's on the other one. So there's one low pressure screw-in switch right on the back side of this that we'll point at. That one has a Schrader behind it because it's not nearly as critical as the high pressure. Low pressure again is the third stage. There's a low pressure setting in here. Then there's a low pressure in each compressor that we can't lower. It's set at 22 pounds, and that one is at 15. Which basically, if that one trips, we're out of gas. So that's the last one. One of the last things we want to see happen here either. So then we have control the cooling fan is just the little computer fan in the back of the cabinet here. It turns on and off based on temperature. Chiller run, chiller fault, and economizer enable. Now chiller fault says on right now because we're not seeing flow. I'm going to program that so that it doesn't look at it when the machine's not being called for. Because every time it's not being called for, right now you're going to go into fault. We don't want that. Mm-hmm. So in a 2-button push, I can have that only look at it when the machine's being called to run. And that'll get any nuisance alarms out of you. I don't know if you're getting reports of alarms back.
Yes, I am.
Yeah, so we'll get rid of that. Okay, so he's only looking at it on startup also, but I'll clear that so he doesn't see those.
Okay.
Below that is economizer enable. So this machine has an economizer on it that is essentially the same that all the other big guys carry and train. They all use a liquid line subcooling to do economizer. So it's just a heat exchanger across the liquid line that acts as a subcooler that lowers the pressure of the refrigerant, compacts and eliminates flash gas, delivers it through the expansion valve a little quicker. And we only use it at 70% of our KW and higher because it saves about 4% energy, but only at the high end. It does very little work, if any, or maybe even hurts you at the low end. But at the high end, we can save 4% energy just by opening a solenoid. It's not bad. There's really no moving parts to it other than the EEV expansion valve. And then we have some outputs that show us the percentage of our expansion valves. Level sensor, which right now reads 23. The level sensor, if you can see, it's right through here. You can see it this way. So it's on, I don't know if you want to see it. It's on the other side of the machine, but it points this way. So we control this chiller by a level sensor, and the level sensor is in the condenser. So we try to maintain a certain level in the condenser, which in turn should be a certain level in the evaporator. And as this goes up, it's going to open the expansion valves to draw it back down. And if it gets lower, it's going to close the expansion valves to kind of pump refrigerant back into the condenser. So when the level's up in the condenser, it's going to open the expansion valves to drive more refrigerant back into the evaporator in order to get that level back to the set point. As it drives more refrigerant back into the evaporator pressure increases because now it's got more refrigerant in it. The compressors are looking at that pressure. So if the pressure increases, the brain of the compressor says we got to run harder to get that pressure back down where it should be. The computer takes temperature versus pressure number and comes up with the number it needs to deliver, say, 44 degree water. So right now it's at 42, but the 42 is actually our hot point. That will go down to like 36 and a half, 37 as we're running. It'll find that spot it needs to be to make that temperature pressure number for suction to boil off that refrigerant. And those compressors speed up and slow down based on this number right here. So if that number, right now let's say that number is 42 in green. If this number 56 is higher, if the 56 is higher, it's going to keep driving that compressor harder and harder and harder to try to get it to get down to that 42 number. If it goes under it, it's going to stop backing it off. And that's how it determines the speed of the compressors. So the level sensor works the valves, the suction set point works the compressors. They all work in one kind of harmony to make this all happen. Let's see. There's really good trending software. Anything happens on this machine gets recorded and including everything that happens today, like nothing today because we haven't done anything. But if I go here, I'm going to change the set point, even though it's 45. I'm just going to make it 45 again. 45, enter. So that's how easy it is to change the set point. So you hit the change set point button, you go 45 or 47 or 42, hit enter. Every time you do it, it's going to say operator change cooling temperature set point to 45 or to 42. Or if somebody tried to put in 9, it's going to say operator tried to put in set point 9, did not accept it because 39 is our lowest. Or it may not even record that. It may just not even give you that option. But
And the highest is 70, I believe.
I believe it is, yeah. If I go 9, enter, see, valid number must be between 38 and 70. So that's our range. So we'll hit OK. I'm going to hit escape. So we still operator change cooling temperature set point to 45. So now I have something to look at today. So this records any fault alarm, change set point, anything that happens this day will show up on this screen, and it's here forever. So, excuse me. We have a memory card in here that stores this data for up to 10 years. And you can, as simple as going back and going, oh, this day was hot, maybe it was running that day. So we find a day, we can see what happened. It says it was open alarm, open alarm, let's see, we have, our first out of alarm is at, it says 1846, what happened at 6 o'clock at night, looks like it turned off for the first time, must be based on demand or temperature, or any of that. And we had a cool, this may even be the day this can't be the first day I was here. I can't be that lucky. Was it? No, that was just last week. I think we started this 3 weeks ago. Yeah, about that. Yeah. So it looks like we had a little flow issues because we got some low pressure safeties, open alarm. We have a couple low pressure safeties, so it may have been some water flow things going on, and a turbo core bearing motor fault, which I'll explain. Oh, that's power down. Because right here we have a turbo core bearing motor fault, and then right below we have Multistack Flex's program started, which means somebody knocked power down and brought power back up. 6 o'clock at night?
No, the problem was that on EMS.
Yep.
It's going to 0, the set point on the
Set point over there for chiller
Okay.
went to 0,
Gotcha.
but here on the machine it was still 45.
Sure.
We couldn't understand why we were seeing 0, so we called ATCO, and they said that okay, just
Cycle power?
cycle power. So when they came in and cycle power, that's what you're seeing.
That's what I'm saying, right?
Yep, and that went to 0 over there.
Okay.
So the control guy tried to explain it, but I'm not the control person. That's too technical that he is looking at that it clears out the previous set point and it goes to default.
Okay.
And the default was 0.
Gotcha. Which is no good.
Yeah.
Right.
But here it stays
45. Okay.
45. And he said that whatever is on the computer, if the power is recycled, machine will run on its own set point.
This stays at last state. So if we lose power there, whatever the last signal to this was, it will stay. So you should be fine. But at least going through this, I can go, oh, geez, we had a power failure. Maybe that's why we had a couple low flow. You know, that low pressure safety now makes sense because it's reading 0 until it gathers data. So it grabs a low pressure alarm. As soon as it gathers the data and sees it's above 0, it comes out of low pressure. So that's why we have a low pressure alarm, and that makes sense. And then somebody tried to change temperatures, like you were saying.
Yeah, we were trying to see that it is working.
So it tells a pretty good story that you can put together with just a couple questions to other people. And now I know that we didn't have a low pressure. We actually had a power down, blah, blah, blah. You try to change some set points. And we can go back any day. We could just keep going back to last year, year before. We could export this to a comma separated value and send it to somebody, send it to me, send it to the factory. They can look at it, read it. There's 2 USB ports right in the back side of the monitor. You can put a USB in, and I will open that up after we stop talking here. So this is great because it shows everything that's happening today and in the past. Then in the user menu, there's a trend. And this trend grabs every data point in the chiller, compresses, temperatures, amperages, kW, speeds. If you can whether a valve opened or closed, solenoid energized or not, every 5 seconds, and we store this data for 10 years. So it's really easy. So from here we have uncheck all pens, nice and clean. I like to take chill water out. I'll usually go condenser water in, so the 2 I really care about. Then I'll take actual set point, and I'll watch what happens with those 3. Those are the first 3 I go at, and then from there I may look at the BAS enable, see if they're taking it away and adding it. That's either 100 or 0 because it's on or off. I can add in amps. If I had outside temp, I could add that, but I don't think we don't have that option on this machine. And I can go look at all day. So that's from the beginning of the day, from 0.00 hours to now, to 9:24. Or I can go to historic trends, and I can go back to trends. We can go to April. Let's see, January, March, April. Open. We can look at last Friday if we wanted to, which I'm going to guess. I don't think that's it. And this will pull up that day's. It's loading right now, that little yellow box, just saying loading data. It may have nothing that day, I don't know. We'll see if it ran or not. No, it didn't run. So that's the whole day for 424. But I could pick any day. I could go back, see the temperatures, see the pressures, see whether we lost chill water flow, any of those things. Then I could take it and I can do the same thing. I can export it to a file, put a drive in. It becomes the E drive because we already have a C and a D. So your thumb drive becomes the E drive. You download it to the E drive. It's a CSV. It's actually surprisingly small, especially if it's only a day or 2. If you want a year, it's going to be a few gigs. Our thumb drive in here is a 32 gig thumb drive, and it'll hold all 10 years on that. So, but it comes in handy. And then I have this program like on my laptop, so I can look at it in this format, or I could take it as a comma separated value and look at it as a giant Excel sheet, really, really big Excel sheet, and 1,300 lines kind of Excel sheet. So, back to main screen. In our main screen, this is pretty much the screen you guys will look at more than not. It's the basics: chill water in and out, towel water in and out, lets you know if a compressor is an alarm, gives you your KW, your capacity. It still gives you this screen up here, so you know if anybody's touched anything. It's just a nice, I don't know if you guys log chillers or not. For logging, it's a great little screen. I've gone to jobs where they're logging the RPMs of compressors and stuff like that. And I'm like, well, we're already tracking all that. We're really tracking this too. So we're technically logging the chiller for you as we go. But this is a nice screen that takes some of that blur away. Like our flow switches, we have no flow, we have no flow. And hit back to this dashboard, and we have back to our screen. So right now, we're disabled because we're not calling. So the interlock to the compressor is open. So the compressor's off. Everything's in plain English. If there's a fault with the compressor, like this may say bearing motor fault across the top, bearing motor fault is 14 items, and 12 of those are minor. Could it be anywhere from when you lose power, you create a bearing motor fault because the power to that magnet, even if it's not being energized, is always there. If the power goes away for any reason at all, it spits out a fault condition on its way down. Just to say my 670 volts DC is now under 500 and I can't run, so I'm going to spit you an alarm to let you know that I can't run. So it comes out as bearing motor fault, and then everybody thinks the sky is falling because it sounds devastating, and it's not. So if you get 3 alarms of the same in a half hour, this compressor will lock out. So if you get 3 bearing motor faults on power fail is the only one that doesn't, because technically it refreshes itself every time you restart. But if you got 3, say, high temp inverter, because your cooling tower was 45 degrees, because somebody tried to run this in February, and what happens is your chill water's at 70 and your cooling tower's at 45, we're in what's called inverted. We can't build a pressure ratio. So if we can't build a pressure ratio, we can't cool the compressor. So what happens is that it'll go off on like internal temperature. If it does that same one 3 times in a half hour, right here it'll say compressor lockout. And the only way to clear a compressor lockout is to kill its power for 3 minutes roughly. There's a board inside here. There's a direct link to the compressor. It's actually part of the compressor. So this board right here is called the compressor in-out board, I/O board. It's got a little green light on it right here. That light is the capacitor bleed for that compressor. When that light goes out, it takes about 1.5 minutes. I just blindly tell people shut off for 5 minutes and don't cheat, and then come back on and you'll be all set. It should go out. Yeah, it's out. So now that that's out, that resets all the hard lockouts on the compressor. And we can then turn it back on. If you turn it back on while that light's still green, compressor will start up again if it's not locked out, but if it had a lockout, it's not going to clear it. So that way, if you ever have a power failure, not every power failure is a minute and a half. Most of them are a second. Enough to take the compressor down and get it to reboot. So that being said, that is our electronics bleed. The chiller's got these 4 big capacitors on the back here. They're about this tall. Those are there in case we lose power and we're running. We need to have some energy in the machine to keep it powered and shut it off safely, so that when we lose power at 30,000 RPMs, we're not just banging that thing all around in there. We want it to spin, stop, drop, and get out. It does it in about 4 or 5 seconds, but it does it with electricity and not relying on safeties or anything like that. So that little thump is the magnet trying itself out for the first time, because there's a lot of wires there. So at least it's all laid out really well. The print down here shows you which sensor we're outputting to. So all these right here are all in line with that. This temperature sensor is the same temperature sensors that are in all Multistack's modern chillers. So your VME, your heater, has the same temperature sensor. Your older machine does not, because it's on a different platform. That's got the old touch box. If you want to take a peek at this, you got to kill power for at least 15 minutes. This will kill you up on top here. And it's not much. It's a good plastic. I've seen insulators walking across these things, and I yell as loud as I can for them to get off, because they don't get it. They think I'm flipping out, but they're going to die. So you get a foot stuck in there with an energized, you're not coming home. I've never seen one break though, which is the other good thing. But still a lot of power. And it's deceiving. I would rather have a big sticker that says 1,000 volts DC on top, and it doesn't have that.